Chris Halsey. I'm an analytical chemistry professor at Westminster College, and it is in fact my great pleasure to introduce our next speaker, Dr. Hakeem Oluseyi. Growing up in the tougher parts of New Orleans, Houston, LA, and rural Mississippi, he and his mother moved around often in the southern United States. He cites early introduction and influence in the sciences from reading specifically the World Book encyclopedias. And if you're not familiar with that, I know we have a younger audience, that's Wikipedia without the internet. That's where he was introduced to Albert Einstein and the theory of relativity. After a short time in the Navy, he began his higher education, at Tougaloo College, earning his bachelor's of science in physics and mathematics. And he tells me a minor in chemistry, by the way. A master's degree and a PhD in physics would follow from Stanford. Summing it up like that makes it sound easy, but in interviews he points out the hardships and the rewards for his perseverance, fueled by the drive to silence his doubters. Through that perseverance, his resume now includes 8 US patents, a professorship in the physics and space sciences at Florida Institute of Technology, being named the Chief Science Officer for Discovery Communications. You might have seen him from a show called Outrageous Acts of Science, a research position at MIT, and most recently, a position at NASA in Washington, D.C. His research focuses on the development of instrumentation for space-based astronomical observation. He is most distinguished in the area of expanding and improving science education here and abroad. He is an astrophysicist, a TV host, a voice actor, an industry mercenary who is problem-solving across all disciplines, not just astrophysics, and simply an inspiration. Please welcome to the podium Dr. Hakeem Oluseyi.
Thank you for that wonderful introduction. It doesn't happen very often that someone properly pronounces my last name, so that's quite an achievement. I'd like to thank you all for having me here at Westminster College. It's a great honor. I recognize whose footsteps I'm following in, so I'd like to thank your president, Dr. Akande, for having me, and his wonderful family for hosting me. I'd also like to thank Professor Kurt Russell and also Professor Halsey for hosting me. So if you look at your program, you might find that what I'm going to talk about is a bit different from what's in the program. And it depends on which program you have. So there's this nice, pretty one here, Audacious Ingenuity, that talks about, that describes my abstract and what I'm going to discuss. And I wanted to talk about innovation because that's the theme this week. So I've been able to innovate in the sciences and in education. And so whenever I'm talking to students, right, I want to make it about you, not so much about me, right? And the lessons that I've learned and how you can apply them in your own lives. Now, when we think about innovation, there's no shortness of innovation in our country, right? We're a country that maintains a lead in science as well as in economics because of the richness of innovation that occurs here in America. But there's a particular type of innovation that I want to talk about that happens in science, and that's when you have these big paradigm shifts, right? When things just change. And this hit me personally, because apparently people like me becoming a well-known scientist is a paradigm shift for some people. There were these articles that were written about me several years ago, and the first article was titled, "Rise of a Gangsta Nerd." And the second article was titled, "The Gangsta Physicist." And I saw these titles, and the first thing I think is, it's not like I'm walking around the lab intimidating people and robbing them anymore. So, why are they focused on the past, right? We don't look at our presidential candidates and call Donald Trump the, wet your diaper presidential candidate, right? We focus on who he is today. And I really didn't understand how this would impact my career either, right? Having a title, the Gangsta Physicist. But one thing happened, some of you mentioned, I talked to students at lunch, and someone mentioned to me that they had saw this TED Talk I did on infinity. Did any of you see that? Yeah, so did you know that talk took place in a prison? Yeah, so it turns out that I was invited to go to this prison, and I was informed over and over again by the host of the event that, Hakeem, you're the only person that the prisoner specifically requested, which was kind of scary. And I didn't understand, why do they want me, all right? And I found out after I gave my talk, I was walking through the prison, and on sight, prisoners would recognize me. And they'd say, hey, the gangster physicist, right? And so for a day in prison, I was a shot caller, right? I was a man in prison. I could order people around. And what I realized happened is that they were using this article to inspire these prisoners, right? They say, look at this guy, look at his past, look at his life, you can do this too. And the statistics of recidivism in California State Prison is really bad, right? For those people who are released from prison, a very high percentage return to prison afterwards, somewhere around 90%. But for those prisoners who received a minimum of an associate's degree, the recidivism rate fell to 6%, from 90 to 6. So they were using this article and the Anti-Recidivism Coalition to help these prisoners with their lives. And so that's another paradigm shift, right? Now, when I think about paradigm shifts in physics, there's something going on right now in the world of physics that is so amazing, I just have to share it with you. Because, you students are the next generation of thinkers, and we look at the way we solve problems in physics, sometimes it takes many generations. There's a saying that goes, the grandparents lay the cornerstone and the grandchildren erect the steeple, right? So here's the foundation that has just been laid. There were a couple of papers published about 100 years ago, and they both involved Albert Einstein. So we've come up with this equation, not me, but researchers come up with this equation that goes ER equals EPR. So ER is the paper by Einstein and Rosen that predicted the existence of a wormhole. You guys know what a wormhole is? Yeah, well, a wormhole is when you have a black hole, and under certain conditions, the black hole can be a portal to another location in time and space. And so you can instantly travel from one location in space to another location that's hundreds or thousands or millions of light years away. And it sounds like science fiction, and it's incorporated in science fiction, but the laws of physics say that this can actually happen. And the problem, though, is that these wormholes are very, very unstable, right? So the likelihood of it was really small, we thought. Now, if you're a scientist, one way that we innovate is through hate. Did you catch that? Through hate. Here's what I mean. There's an example from history where in the 19th century, there was a question of how does the process of diffraction work? So we knew how reflection worked, we knew how refraction worked, but what is diffraction? The most common example, I think, that where you get to witness diffraction is when you see oil on the surface of water, you see this rainbow pattern, right? What is the light doing to make that happen? So the French Academy of Sciences held a contest to solve that problem, and a gentleman named Fresnel submitted an essay, and that essay relied on the fact that light travels as a wave. Now, physicists did not think that light traveled as waves. They thought, as Isaac Newton thought, that light is a series of particles, right? So Fresnel submits his essay, and on this panel as a judge is Poisson, the mathematician. So he says, yeah, this looks elegant, but I know it's wrong. So what am I going to do? I'm going to take these equations, and I'm going to see if they predict anything that I know cannot be true. And he found something. He found that if you were to take a round object, a circular object, and take it into a dark room and cast a light on it, that in the center of the shadow of that object, there would be a spot of light. Now that is obviously ridiculous. A shadow is darkest in its center. But also on the panel was an experimentalist named Arago. And he said, well, I never thought to do that experiment. Let me take a round object into a dark room, cast a shadow, and see if the spot of light is there. And what do you think he saw? The spot of light was there. So that phenomenon became known as Poisson's spot because he discovered it in the equations, although he was attempting to hate on the theory, right? So Albert Einstein did the same thing. In the early 20th century, quantum mechanics had come about, and quantum mechanics was very different from his general relativity. And so he thought, well, let me look at this quantum mechanical system of equations and see if it predicts anything that I know cannot be true. And he found what he called a spooky action at a distance that we today call quantum entanglement, right? And so a paper was written by Einstein, Podolsky, and Rosen EPR. And so we have this equation, ER equals EPR. So let me explain this quantum entanglement to you. Suppose I have a twin, and when we're born, we share in existence. We are entangled. And so due to our state of entanglement, whenever one of us is sitting, the other must be standing. And we sit and stand really fast. It happens on like a trillionth of a second. And there are people who can measure whether or not I'm standing or sitting and whether or not my twin is standing or sitting, and they can do their measurement down to a millionth of a second. And let's say, for example, that throughout our lives, I have 3 people observing me, and there are 3 people observing him, and they keep records to the millionth of a second when each of us is sitting and standing. And then I decide I'm going to leave planet Earth. I'm going to go to Mars. And my observers come with me, and they keep the records. And then I decide, well, you know what? I hear there's a new planet around Proxima b, so I'm going to go there. And they continue to keep the records. And then I decide, well, I'd like to go 2 million light years away to the Andromeda galaxy. And they continue to keep these records. And then after maybe 50 years, the observers get together, and they compare their records. And what they see is down to the millionth of a second that this is held true. Whenever one of us was sitting, the other was standing. How could that be? Because in order for me to know when my twin is sitting or standing, or my twin to know when I'm sitting or standing, a signal must traverse between us. So how could it happen instantaneously when we're separated by great distances? Because that's what space is. Space is what separates here from there. The reason you're seeing me right now and I'm seeing you is because light is traveling between us. I'm not seeing you as you are now, but as you were some tiny fraction of a second ago, right? So how could they be communicating? So in the 90s, quantum entanglement was actually measured for the first time. It's a real phenomenon in our universe, right? And physicists have been trying to get their mind around how could this communication be taking place. But then not long ago, it was recognized that quantum entanglement and wormholes are perhaps the same phenomenon. Now that is mind-boggling, because in order to create a wormhole, an Einstein-Rosen bridge, it takes an incredible amount of energy and mass to do that. These entangled particles are single elementary particles. Could they possibly be connected by wormholes? That appears to be the case. That appears to be true. So what does that tell us about the space in which we live? What does that tell us about space at all? So this isn't something that was unforeseen. The science fiction writers had a problem that they had to solve. So if you're in the Starship Enterprise on the other side of the galaxy, 1,000 light years away, or 40,000 light years away, how do you communicate back with Earth instantly? And the communication not take 40,000 years, right? Well, they invented this concept of subspace. You guys familiar with that? Where are my nerds in here? Can the nerd section raise your hand? We're nerds, my nerd. All right, there's my nerds over there. Right, so they created subspace communication. So what does this have to do with innovation? Well, the theme of the innovation that I'm looking at and that I'm considering is looking at the old, but looking at it anew. So these papers existed for 100 years. We knew about these two phenomena, and only recently have they been connected. And now this is about to transform how humankind looks at space. How are we going to take advantage of this in the future? What are going to be the new technologies that are going to take advantage of perhaps this subspace communication? Another example that's really similar, when Albert Einstein came up with his special theory of relativity, we learned that time is not something that is absolute. How time passes to you in comparison to me depends on our relative motion and also the differences in gravity between us. For example, when you're in space versus being on the surface of the Earth, time moves more quickly. Now, when Einstein looked at it that way, Einstein looked at it and said, well, when things move fast, distances get shorter. When things move fast, time passes more slowly. But in the modern times, we have a new interpretation of it. And the new interpretation of it is this: at all times, everything in the universe moves at the speed of light. So right now, you're moving at the speed of light and I'm moving at the speed of light. Do you feel it? No, you don't feel it? Here's why you don't feel it. Because we are at rest relative to each other in space, we are together moving through space, moving through time at the speed of light. But if one of us was to take off going really fast through space, then because you must move at the speed of light at all times, you must move more slowly through time compared to the rest of us. So the exact equation is that the speed of light squared is equal to your speed through space squared plus your speed through time squared. Now, here are some consequences of that. How can I take advantage of that? Let's do an experiment. Have you heard of the twin paradox? So in the twin paradox, it's exactly as I said. I have a twin, and one of us leaves Earth moving at very high speed. Time passes more slowly for the traveling twin. They travel for some time, come back to Earth. For them, maybe 10 years have passed, but on Earth, maybe 1,000 years have passed. And this is a real phenomenon that we measure all the time in the laboratory. So how can we take advantage of that today? Well, there's one measurement that we wish to make. You've heard that the universe is expanding, correct? And so there's many evidences that point to this. But the thing we have not been able to observe is the universe expanding in real time. Can we see the expansion change? Can I observe the redshift of a galaxy change? What we call Z dot, for example. So imagine the twin experiment done in a different way. Suppose there is this light that fills all of the universe. And because the universe is expanding, as the universe expands, that light gets stretched out by the exact same amount that the universe expands. Well, it turns out that that actually exists. We call that light the cosmic microwave background radiation. Okay? So my twin and I measure the wavelength, some characteristic wavelength of this microwave background radiation. And then the twin goes and travels at a very high speed relative to me and comes back. And we both measure the wavelength again. And so we get what a scientist would call delta lambda, the change in the wavelength. But then we can also both measure the change in time between those two measurements. So for the twin who stayed home on Earth, the time is big. And so for the twin who was traveling in space, the time is small, right? So obviously we measured very different results for how fast that light was changing its wavelength. Are you with me? Yeah. So what does this tell me? This tells me that if I want to do this observation that physicists are trying to do right now, every day, of observing the changing of this light that fills the universe, or the measurement of a galaxy moving away, then all I have to do is move at a very, very high speed, and then I can observe that perhaps in a human lifetime. Whereas our current ideas would take much, much longer. So these are deep, very abstract ideas of how we can use innovation. But in my work as a professor, right, I judge these student competitions. And with my role with Discovery, I help to judge the Discovery 3M Young Scientist Challenge. And what I see happening now is students, just like yourselves, are looking at the technology that has been around you and saying, how can I repurpose this technology to solve a problem that exists today? But it really depends critically on defining the correct problem, right? So let me give you an example. One problem that people have is safety. So suppose you work late and you have to go out to your parking lot, go out to the parking lot to get in your car at night, right? So if you talk to a police officer, they will tell you that parking lots are very dangerous places. So how do you know that you're going to be safe going to your car? Well, now cars are equipped with cameras, right, to help you back up. So this student said to me, what if I build an app that will allow you to use your phone to turn on the cameras around your car to determine if you're safe going to your car at night? All right, that's a wonderful innovation. Let's take what already exists and let's repurpose it for something to solve a current problem of today. Now, another way that we can innovate, when I look at my own life of innovation, as a scientist, as a student, you become an expert in a particular field. You're studying some phenomenon and you become really intimate with it, right? So when you become a PhD student, for example, your first job is to become current in your field. That means that you take everything on your topic that has ever existed and you read every paper you can, especially from all the top scientists. And now that you know what everyone else has said about it, it's time for you to add, to contribute to this knowledge. Right? It's time for you to give something new. And that's when you receive your PhD, when you make that new contribution. And so we have a saying that goes like this: becoming an expert means knowing more and more about less and less until you know everything about nothing. Right? And it's kind of close to true, but here's something I found. When I was a graduate student, I was studying solar physics. I was studying processes that occur on the surface of the sun. You've seen these pictures of the sun with the plasma loops and the hot X-ray gas. I was on the team that took that technology and applied it to observing the sun for the first time. And here I am studying the sun and what's happening there, but when I go to get a job, I don't go to academia, I go to Silicon Valley. And I go in Silicon Valley and I'm working on solving this problem of efficiency in making computer chips. So here's what happens. When you make a computer chip, there's many steps. Some steps deposit material on a silicon wafer. Some steps remove material on the silicon wafer. Some steps create patterns on the silicon wafer. And every step, you need to know how well it works. Because if I have a big, giant, silicon disk of expensive computer chips, I better make sure I got these processes right or I just lost a ton of money. So what they do is they put in these wafers that are called test wafers. And so you do the process on that test wafer and then you take it out and you measure to see if the process happened as it was supposed to. All right? And if it didn't, you throw away the wafers. Now, at the end of all the processing, you test certain chips. And every time you test the chip, you destroy that chip. It cannot be sold. So there's a lot of waste going on, and there's no way to make sure in real time that, you make the process happen properly. You can only tell after the fact whether or not it did. So I step into Silicon Valley, and I work on a team that wants to address this problem. How can we get rid of these silicon wafers? How can we make sure that every process works as it is supposed to in real time? And I look at the problem and I say, oh, you know what? In astrophysics, we have a way of measuring light that comes from objects and being able to tell all these physical characteristics of what's going on inside that star. Think about it. A star, if you ever look at a star through a telescope, it looks exactly like it looks to the naked eye, right? It's a dot of light. But if you ask an astrophysicist about that star, they'll say, oh, it has this chemical composition, it's this temperature, it's moving in this way, the star is this age. How do you know all that from a spot of light, right? So let me give you the answer and get back to the innovation story. If I were to ask you guys, what is matter made of, what would everyone say? Atoms, exactly, everyone knows that. If I were to ask you, where does light come from, what would you say? Speak up, or everyone gets an F. The sun, I hear that all the time. There's no sun in this room, but I see a lot of light. Where does it come from? Where does light come from? Well, let me give you the simplest answer. It comes from one place. Matter makes it. Right? Matter makes it. Every example you can think of, matter is making the light. But here's the amazing thing. When matter makes light, the signature and of the identity of that matter is encoded in the light, and what that matter is doing when it made that light is encoded in the light. And if that light travels through space, the dynamics of space, whether space is expanding or contracting, is encoded in that light. So when I had this problem of trying to figure out what was going on inside of these chambers, I thought, well, look, many of these processes that deposit material and remove material, they use plasmas, and plasmas emit light. So all we have to do is monitor this light and we can figure out everything that's going on in real time. We can make corrections in real time and problem solved. And you know what happened? Guess what my bosses said? Ah, that wouldn't work, right? So what I did is I went on ahead and developed the technology anyway. And I ended up having we had a performance review at the end of the year. And my manager gave me a less than favorable review, right? And because I didn't do as I was told, instead, I went in and developed this new technology. And that new technology resulted in a completely new division of the company, right? It was very profitable for the company. I got several patents out of that particular technology. And I had an argument with my manager in the parking lot about this. And I said to him, I was like, look, you are comparing results with activities, and results matter more than activities. And he changed my grade and he raised it to a very high rating. But the second point in innovation is this: you're gonna come across naysayers, right? You're gonna come across haters. Hate can be a crucible for creating and innovating, or it can stifle it in its tracks. And we're all humans, we're all a part of this human tapestry, and we play different roles. Sometimes you're the person in the lab that's doing the work, you're intimate with the work, and it's because of that intimacy you can make the connection between astrophysics and semiconductor manufacturing. I have a graduate student. He was working on this problem of how the sun creates the solar wind. How does the sun accelerate particles, away from itself, given the sun's very strong gravity? It accelerates particles at up to 800 kilometers per second, the high-speed solar wind, and sometimes even 3,000 kilometers per second, right? What if we could do that? That would give us an in-space propulsion technology that's almost 100 times faster than anything we've even perceived of today. And I told him, I said, listen, always pay attention to what's going on in areas of science that are related to what you're doing, but not what you're doing. So he paid attention to plasma experiments in the lab, which are very different from an astrophysicist's plasma laboratory, which happens on the surface of the sun or in stars. And he realized that, well, look, there's this one configuration that the sun uses to create these high-speed plasmas, and now the plasma physicists who do this stuff in the lab have created a technology that will allow us to build what the sun does in a little tiny chamber. We can make it really small, we can make it really big. And so now that has become a new patented technique for in-space propulsion, right? And that is from seeing these relationships and having this intimacy. But here's the thing. One day he came to me and he said, hey, Dr. O, I have this idea. I noticed that the plasma physicists have done this. Do you think that maybe we could combine these two ideas and create an in-space propulsion technology? At that point, I was in the position of my manager in Silicon Valley, right? I could have said, go for it, or you're out of your mind. Now, being the open-minded guy I am, I said, go for it. What if I had not said that? What if I had told him not to go? You don't know if the person you're talking to is going to be someone who is going to say, well, I'll show you, as I did, or if they're going to be someone who's going to say, yeah, I guess I really am dumb like I thought I was, right? You guys just don't ever laugh at my jokes. I'm never coming back to, well, I'm going to come back, but I'm going to make sure they get everybody's name and, bring the fun students into the talk. Listen, guys, I'm making jokes. You got to identify that and then laugh at them, okay? It's an important part of this process. So the point here is that in innovation, there's many paths to innovation. There are many roles in innovation, right? When you're the leader, how do you bring innovation out of the people that are working for you and along with you? When you're in the lower role and you know that you're on to something, but the people above you don't support it, what do you do then, right? My answer is you believe in yourself and you do it anyway. And my other answer is that you have to also believe in others and see it in them. One of my, and that brings me back to another point. Now, this is a warning, a joke is coming up, okay? But it's not really a joke, it's a true story. A couple of weeks ago, I was talking to my mother, right? And I was talking to my mother, and she was telling me, she was like, you know what, there's something weird that's happening now. Whenever I talk to some of my old friends that knew you when you were young, and I tell them what you're doing now, not the TV stuff, but the scientist stuff, they go, him? Really? And I say, Mom, why do they think that? She goes, because you were always joking. You were joking all the time. You were never serious. People don't think that a person who jokes around a lot can actually be serious, right? And what that reminds me of and what that makes me think of is how we judge each other as human beings, right? And how, as I go around this country, as I go around this world, there's one thing that stands out to me, and that is how we are definitely not taking advantage of what we have as human beings, our human capital. There are so many people that could be contributing to this enterprise that just are not. And I've narrowed it down to a couple of things that I think are key. And the first one is identity. So as an example, when I was a young man, at that time I was a young black man. That was a joke. And I thought, the world told me, oh, here's who you are and what you are. And so for me, I had to be intimidating, right? I had to be great at basketball. I had to be a ladies' man, right? And I was all those things. Hey, you caught that one without a warning. That was good, right? But, I didn't see myself in, as the master of mathematics, for example, and I wasn't, right? And now, as I see people, even as a professor, I've been guilty of this. I had this student who came to me. I'll tell you his name. His name was Patrick Champy. This guy, he was a big guy. He had a scar across his face, and he just had this sort of intimidating demeanor. And he's like, Professor Oluseyi, I want to work with you. And, I'd say something to him like, oh, well, I don't have any openings. But in my mind, I'm thinking, man, you look scary, right? And I had him in a class, and he was about a C student, right? And finally, he just pursued me. And I allowed him to join my research group. That undergraduate turned out to be one of the greatest leaders I ever had in my research group. And he taught me a lesson about judging people and what they're capable of. Now, he's at Marshall Space Flight Center in Huntsville, Alabama. He's building rockets, and as a graduate student, he's working as a leader as if he already has a PhD, right? And so I've gone all across the continent of Africa, and I've gone into the slums, I've gone into Cape Flats, right? And I see everywhere that there are people who are like me who thought to themselves, oh, I'm a female, oh, I'm from the slums, I'm a colored, like in South Africa, or, and because of that, they don't see themselves in the role of the scientist or a person who can even do that science. And that is one of the most amazing things about going on television that has happened to my life, is because now I go around the country and every day I get recognized by people, and there are so many people that are from backgrounds like my own who come up to me and say, man, seeing you on television, when I hear you talk, I get it. And I see that it's cool, and I realize that I can do it too. And so many people have told me, because of you, I'm going back to school now. And so that is a type, in my mind, of social innovation, because you see all these people who at one time, they were living in a paradigm of who is supposed to do this and who can't do this, what I'm supposed to do and what I can't do. At Florida Tech, the students used to joke, and these are the students, we have everything at Florida Tech. Florida Tech is really good when it comes to space, sea, and sky, right? And so when it comes to the ocean stuff, we wondered, why do so many of the young women go into studying dolphins? What is it about that, right? What is it that makes us think that, here is my place and here's this other person's place? Like I was talking to my mother, again, I was in Silicon Valley, and when I was in Silicon Valley, you work in these groups. There was one time I was the only non-Korean member of my group. There was one time I was the only non-Chinese member of my group. There was one time I was the only non-Indian member of my group, right? And so I was telling my mother this, and she said something about, oh yeah, you're working with those smart people. And it was the stereotype of Asians being scientifically smarter and mathematically smarter. Have you guys heard that stereotype? Do you think it's true? No. Hey, trust me, if I was Asian, I'd be, yes, it is, right? And we're better at everything else too, right? But yeah. But the truth of the matter is that because I had worked with so many people, I forgot that stereotype even existed, right? Because it's definitely not true, right? Everybody has the same capabilities. And so identity is one element, but the other element is hierarchy of humanity. That is something that our generation needs to get rid of, right? We all know the hierarchy. Like, let me ask you a question. Do you people think I'm a nice guy? Yeah, I'm the nicest guy in the world. You think I'm dangerous? On the basketball court, but otherwise, I'm really good. Now, I can't tell you how many times I'm in an elevator, the elevator door opens, and there's a single lady with her kids. The kids start getting on the elevator, and the lady stops them. We'll get the next one, right? These sort of things happen to me all the time. Why is that? Because I'm under suspicion. Because there is this hierarchy of humanity, and we know who is who and who isn't who, but you know what? It's completely bogus. It's completely incorrect. And because of that, people like me, the chances of me not standing here today were so high, it's ridiculous. Do you know why I'm standing here today? Because I couldn't be a bellhop. Does that surprise you? I wanted to be a bellhop. Let me tell you how this happened. I was at Tougaloo College, and I thought I wasn't smart enough for college, and I dropped out of college. And I was working as a janitor at the Ramada Renaissance Hotel, and I was making $4 an hour and barely making $100 a week. And the bellhop got fired. Now, a bellhop can make $100 in a day in tips. So I applied for the bellhop position. And the managers looked at me and they said, Hakeem, the janitor, you are not bellhop material. And I thought to myself, I can't move up from janitor to bellhop? I better go back to college. And I did. And I didn't really understand the power of that story until a few years ago, one of my graduate student friends reminded me of that story. And he said, Hakeem, when you told me that story, the part I didn't see is that he's like, whoever that manager was, they didn't realize that standing in front of them was really a Stanford PhD physicist. But the way they looked at you and the way that they judged you, you weren't even good enough to be a bellhop in their eyes. And yet, look at who you are and what you are today, right? And so I say this because we're all a part of this human tapestry, and especially us professors. There are people that come into our offices, there are these students, and you might think that this person doesn't have it, that person doesn't have it, but that's not our job, right? We're all in this thing together. When you become an astronomer and astrophysicist, you begin to look at the Earth, and you begin to look at our species as one whole. And you begin to realize how perilous a universe we live in, and how we need to get ourselves off of this planet. We need to develop technologies. And the only way we're going to be successful is if we bring everybody on board. And right now, there are whole continents of people that are being left behind, and that's completely unacceptable, right? We have to do better. And so I've gone around working with students, and one thing I've just done is I've been looking at different ways of educating people. So Outrageous Acts of Science has been wonderful because in my classrooms, I've always used humor. And because the students are typically closer to me, they actually do get my jokes, unlike people in this room. And humor has been wonderful, right? Humor has been really wonderful. But also I've learned about experiential learning, right? Learning by doing. Taking the old and looking at it anew. So for centuries upon centuries, humans learned by doing. And now we've come to the point where you sit in a room and you get lectured to, right? Or we give you a piece of technology and we say, go off with this technology and do that. But through games, I'm learning that you can really educate students stealthily. Just like with Outrageous Acts of Science, I can stealthily teach you. You're having fun, you're laughing, but then you're learning at the same time. So I have a young son, and I'm teaching him stuff, right? He's doing excellent in math, he's doing excellent in certain sciences, but one thing I thought was really difficult to teach, and that is chemical reactions, right? Chemical reactions are kind of weird, right? And if you're taking general chemistry right now, or organic chemistry, even worse, you know what I'm talking about, right? But I work with this company called Dig It Games to create this game where we create a really fun scenario where you're going to go to an exoplanet in order to save humanity, right? We have to get humanity off Earth, right? So we're going to go to this exoplanet, but all along the way, the kids have to solve these games, right? So by the way, in case you're wondering, the game is called Exotrex, $5.99. All right. But the game allows the students to learn through experience. Now, I want to say this one last thing that has to do with this hierarchy thing. There's this really controversial book called The Lucifer Principle by Howard Bloom. Has anyone heard of that? And it has to do with human evolution. And he starts with the question of, why do humans do this really crazy, awful thing called war? Right? Why do we do that? That is a horrible thing. And he says, well, it goes down to a couple of characteristics that humans share with many other species. And one is what we call kinship selection. And the other is pecking order, hierarchy, right? Everybody wants to be the top of whatever it is. In classes, in groups, in larger groups, between groups, there is this hierarchical fight. And so to be the top, we will, kill each other. And then also in the social sciences, when we look at the prevalence of hierarchies in society, they talk about what is called last place aversion, right? So you come into a society and there's a hierarchy that pre-exists and you're new into the society. What do? Well, you hate on the bottom of the people at the bottom of the hierarchy, so that you yourselves are not at the bottom of the hierarchy, right? And that's a very dangerous thing. And these hierarchies are different everywhere. I remember when I first left Mississippi, after being there for middle school, high school, and college, and I was at Northern Arizona University, and it was the Sugar Ray Leonard, Tommy Hearns fight. You guys know those people? Yeah. And I was sitting in this room. I was in the West, Northern Arizona University, and I was looking around the room and I was going, wow, look at this. And the reason I felt that way is because it was the United Nations in that room. It was people of all races in that room just hanging out as if it was no thing. Something that never happened in Mississippi, right? I didn't even know that was possible. And yet, here it was right before me. And so I remember approaching, there was an interracial couple, and that just blew my mind, a black guy and a white. I was like, whoa. So I asked this girl, I said, you guys would date a black guy? And she's like, yeah. But then she goes, but I wouldn't date an Indian, talking about the local Navajo Indian tribe, right? And as I've gone around the world, I see that in different societies, there are different hierarchies. Right? Different groups of people at the top and the bottom. Sometimes it's based on race, sometimes it's based on religion, sometimes based on ethnicity. And one social innovation that we need to figure out, I don't have an answer, is how to get rid of these human hierarchies. And it's not until we are able to do that all these problems we're seeing happen in our country right now, and this problem we have that people aren't a part of the enterprise, that people's identities don't fit into the enterprise, we're not going to solve those problems until we solve that problem. And so, as I said before, there is no shortage of innovation, right? But the real problem is identifying the right problem. And once you identify the right problem, and when humans set their mind to solving problems, we typically find an answer, right? So that's it. Thank you very much.
Thank you very much. This is the time for questions, plenty of time for questions, so please step to the mic. All at once.
And remember, you can ask me anything about the universe.
Hi, my name is Leticia. I'm from East Timor and I'm majoring in environmental science. Last week we discussed it in the class and we also read about the articles about the physicist stuff, and I saw your name there. And I'm really curious about the project, the One Telescope project in Africa. And the first time when I read that, the question that came to my mind was that why you want to like distribute those telescopes in every country in Africa.
Yeah. Well, you know, it addresses many things. There is a scientific need, right? So if the science of astronomy has recently undergone a revolution. So what we've used to do is you take a telescope, you point it at an object that you're interested in taking data on, and you take some snapshots of that object. And now we've opened the time domain. So instead of looking at individual objects, you have a telescope that looks at a region of the sky, and then it takes an image there, and then it goes and takes an image of another region, and every night it does that over every region, over and over and over and over again. And over years, you get a movie of that region of the sky. And in that movie, you can identify objects that change brightness, you can identify objects that move, and in each case, you get a different type of incredibly valuable data. But because this is a new science, the top leading edge projects that did this, like HatNet, which is a planet discovering array of telescopes, they're tiny, they're this big. And so anybody now can do this science. You don't have to have a giant telescope. Now, that is the technical feasibility. So I decided to ask myself, so I was working for over a decade, and I partnered with various institutions, the United States State Department, the government of the Netherlands, the governments of Kenya and South Africa, the South African Astronomical Observatory, universities, and NGOs to help develop science education and science research in developing nations. And so when you have people engaging in science that did not previously engage in science, it changes their identity. It now becomes something that they own. For example, when you go into a classroom and your professor teaches you Newton's laws, you think that that professor is Newton himself, right? Because that person owns the knowledge. They didn't invent the knowledge, but they now own the knowledge. And when anybody owns the knowledge, they become that knowledge. And there's so much that does within a society. So why is it that if you're in Kenya, you're buying a cell phone from someone in Norway? Why doesn't it go the other way around? Now, when we talk about the scientific opportunity, most of our resources are in the northern hemisphere. The northern hemisphere sky compared to the southern hemisphere sky is like comparing a lightning bug to lightning. In the northern hemisphere, the center of the galaxy is never very high above the horizon. In the southern hemisphere, the center of the galaxy is directly overhead. Not only that, our two large satellite galaxies, the Clouds of Magellan, are high in the sky, and they are a treasure trove of scientific data. So as a species, as a planet, as a planetary family, we need many, many more telescopes in that southern hemisphere region where there are darker skies and there are greater scientific opportunities, and at the same time, we can transform societies. In fact, my colleague at Florida Institute of Technology, Dan Bachelor, he just wrote a book and he titled it, he's a British scientist, and he titled it Astronomy Saves the World. And it addresses this phenomenon of how astronomy actually transforms people and societies when they participate.
Thank you for your answer.
Thank you for your wonderful question. Yes, sir. I always make people shy. It's all right. So I'm really pretty, so.
Related to quantum eraser experiment, do you think we'll ever be able to come up with a device that's capable of doing something as ridiculous as sending messages back in time?
Ooh, that's a good one. Can we ever? So sending messages forward in time is easy. Sending messages backwards in time. So here's the thing about this wormhole phenomenon. So the idea that quantum entanglement involves this wormhole-ish subspace communication really opens possibilities. Because when we talk about a wormhole, you can go in and come out anywhere, but you can also go in and come out any when, right? So there is the possibility that, these things that were completely ridiculous, the possibility has now been opened that maybe it's not so ridiculous. But the thing about science, one of the greatest lessons I learned in my education was the difference between when you know something and when you don't know it, right? And I can say that to you, and I've never talked to a person to whom I said that, and they didn't instantly put themselves in the, oh, I know the difference, of course, yeah, sure, right? But clearly, people, it's a very difficult thing to really grasp. And so even though we write these things down, and there's nothing in the laws of physics that prevent it, and there's even this principle called the principle of totalitarianism that states that any physical process that's not strictly forbidden to occur in nature must occur. There's evidence that says, okay, well, perhaps this could occur. We don't know if it will occur. So what I've seen is that people who say that something is impossible and it hasn't been proven to be impossible end up looking like idiots in the future. So I'm not going to say it's impossible. Right now, I'm skeptical of sending messages into the past. But, I don't know, right? And I know that I don't know, which makes me know that I don't know, if you know what I'm saying. So, yes, sir. Thank you.
Hi, my name is Khaled. I'm a
Hi.
psychology major, and I was wondering, one of the twin paradox that you mentioned, scenarios in which one of the twins would stay here and the other would travel in high speeds out into space. The second one would be spending 10 years, while the first one would be spending like around 1,000 years. I was wondering, is this process reversible, in which when the second one comes back,
Yeah.
spend 1,000 years, can he go back in time to where his
Well,
first one was?
what you can do is that if they change positions, then when the second one gets back, they will be in the same frame now, right? They could be the same age. Yeah, no, I've never heard anyone come up with that. That's really good. Yeah, catching up with the twin, catching up with the traveling twin. You know where I thought you were going, because there is a part of that story that's left out. What is it that makes the one traveling the one that doesn't age very much versus the one that stays here, right? Which determines which is which? And the answer is acceleration, right? Yeah. Great question. Thank you. See, psychology, he twisted my mind. Yeah.
Hello, my name is Isaac Newberry. My major is environmental studies, and I'm from St. Louis.
Hi, Isaac Newberry.
Yeah, I actually got that one.
I'm sure. Yeah.
Anyway, I was wondering what exactly are your thoughts on the validity of the nemesis theory?
Interesting thing. I know well the guy who came up with the nemesis theory, Rich Muller. And, nemesis is kind of dead now, but there's something that replaced it. So if you don't know what the nemesis theory is, so Rich Muller was his mentor was Louis Alvarez, who was a Nobel Prize winner. And Louis Alvarez's son was the person who discovered the KT boundary layer, this iridium layer, right? And that was a strong piece of evidence that the dinosaurs were wiped out by asteroids. So Louis Alvarez's son had showed that, look, if you look at the extinctions on Earth, it appears to be a periodic cycle of extinctions that occur every 26 million years, right? The last one was 13 million years ago, then 26 million before that, and 26 million before that was the dinosaurs. But that periodicity with more data seems to have disappeared, right? But the nemesis idea was that, well, how could something wipe out life on Earth periodically that way? So Rich Muller said, well, what if the sun is a part of a binary star system, and the other star is a very small, very dim star, like a brown dwarf? Then every so often, perhaps it would pass through the Oort cloud, this cloud of comets that surrounds our solar system, and it would disturb the orbits of the comets, and some will get expelled from the solar system, and some will get sent to the inner solar system, and some of those that were sent to the inner solar system would strike Earth and wipe out all life, right? So nemesis is now dead because the periodicity disappeared, but people have been studying this Oort cloud and the Kuiper belt before the Oort cloud, and objects are now being discovered that are kind of large. So there was an object discovered called Sedna, which we thought was larger than Pluto until we actually went to Pluto and actually measured its radius up close, and it turns out that Pluto is actually a bit bigger than Sedna. But also in Sedna's orbit is an object called Biden, not named after our vice president. And why are these two objects in the same orbit, or these very similar orbits? And then other objects were discovered with similar orbital characteristics. What could cause this? And so the idea is that there is a large object, which was many times more massive than the Earth, that we now call Planet 9. Planet 9 has not been confirmed, but there is evidence that suggests it may be there. But just as we thought we had recently discovered a new particle at the CERN, at the LHC at CERN, right? With more data, the signal may disappear, and we don't know. But the idea of having large objects in the outer solar system that are undiscovered is a valid idea. Great questions.
This is the final question for Dr. Oluseyi.
Seriously?
Hello, I'm Cole Saylor, and I plan on studying both physics and philosophy. I have a question about quantum entanglement.
Yeah.
And I was wondering, for a while now, since the theory of relativity states that data cannot move faster than the speed of light. And since you answered, okay, I'm misunderstanding there. Something along those lines.
There's something subtle, but let's go ahead, yeah.
Your answer was a wormhole.
Right.
How does a particle go about that?
Right, so the idea, the speed of light limitation is so here's what we have in our universe. If you possess mass, you can never move at the speed of light. If you have no mass, then you must move at the speed of light. Nothing can move through space that has mass at the speed of light. There are these theoretical particles called tachyons, which jump over the speed of light and move superluminally, faster than the speed of light. Now, there are some tricks to get around the speed of light. Take warp drive, right? So with warp drive, you don't actually move through space. What you do is you change the shape of space to make it appear that you're moving through space at faster than the speed of light. So warp drive is now a serious concept, right? So a scientist named Alcubierre came up with what is known as the Alcubierre metric, where you can have a spaceship, you can contract space in front of you, expand space behind you, and actually move at 10 times the speed of light through space, right? And then it was modified by someone named White so that it doesn't take as much energy, and it now becomes the Alcubierre-White drive, and White now has a lab, I think in Houston, where they're actually testing this concept. So when we talk about these quantum entanglements and wormholes, you're not moving through space. So when us cosmologists think of space, we think of it not as this 3D volume, but as a 3D hypersurface. And so a surface can be bent, right? So the classic example is this surface is space, and if I fold space, right, now instead of having to travel this great distance to go from here to there, if I fold space, I can just go from here to there. So it's almost like moving through a different dimension of sorts, right? So it's this, so in warp drive, like what Star Trek does, imagine you're in a room and you want to get to the other side of the room and there's a carpet, and you bring the carpet toward you and you crumple it, you warp it, right? And then you just step over the crumpled carpet and then allow it to expand out behind you. And now, you know, I took one step and I was on the other side of the room, essentially, right? But only because I compress space in that way. Yeah. And that's the beauty, man. You know, when I was doing my studies, there was another guy who was a philosophy and physics major, and he was from a wealthy family, and he never intended to work as a physicist, but he just wanted to think as a physicist, and you know, and combining it with philosophy was a wonderful, excellent idea. So I look forward to hear what you're going to be thinking about.
Thank you.
Thank you.
So that's not the final question, because tomorrow, let me please point to your, there you go, tomorrow in the lecture hall in Culture Science Center, specifically at 10:30 tomorrow, he'll answer even more questions for you one-on-one. So please come to that tomorrow. Thank you one more time, Dr. Hakeem Oluseyi.
Thank you all.
We all have goals, ambitions, something that drives us to be great. And with any goal, there are challenges. But challenges can be blessings. Challenges can inspire you to do something extraordinary, whether it's digging deep to make one more play, or working around the clock on a big project. Challenges bring the best part of us to the surface. When Westminster Hall burned down in 1909, the college turned a disastrous event into a proud tradition. Each year, new students and graduates passed through the columns that survived the fire. Over the years, the spirit has served us well as we worked to become an institution that provided a transformative education. Westminster's prestige became known well beyond Fulton, as we were selected as the site for one of the most pivotal addresses of the 20th century. So, how do we go from success to significance? Drawing from our storied past, we will redouble our efforts to make Westminster one of the premier liberal arts colleges in the country. We will challenge our faculty to foster intellectual curiosity and excellence among our students. Students come to Westminster to learn how to become leaders, and faculty play a key role in igniting their passion for learning. We will challenge the students to think not only about their coursework, but also about their place on a global scale. And as a college community, we will challenge ourselves to constantly ask, how can we make this special place even better? Westminster College has a celebrated history and tradition of success. It's time to do something significant.